In Lesson 3.1, we will be discussing exponential functions. In Video 3.1.4, our learning target will be for students to solve problems involving exponential growth and decay. Before we get to start solving problems involving exponential growth and decay, we're going to discuss several formulas that involve using exponential growth and decay in real-world settings. The first function or first formula we're going to discuss is the compound interest formula. And in the compound interest formula, if a principal P is invested at an annual interest rate R in decimal form, compounded n times a year, then the balance A in the account after T years is given by the following formula. A equals P times parentheses 1 plus R divided by N raised to the N times T power. Now, there's several variables in this formula, and we're going to discuss what each of those variables mean. A is the amount, I'm going to abbreviate amount AMT, in the account, ACCT's account, after T years. P is the principal. The principal is the amount originally invested. We'll call it the original amount of money. And R is our interest rate. And it tells us to put in R in decimal form. That's our interest rate. So, for instance, if we had 5% as our interest rate, then we would plug in 0.05 for R because we have to convert it to a decimal. N is the number of compoundings. Now, compoundings is how many times your interest is calculated, how many times a year or annually the bank or the company pays interest on your account. And that should be it. And T is time in years. Now, there's one thing I want to mention before we move on to the next slide is the number of compoundings. Okay, if you are only paid interest once a year, that's called you're paid interest annually, once in a year, annually is yearly, that would mean N equals 1. Okay, if N was 4, that's called quarterly. If you had interest paid to you monthly, that's N equals 12. And if you had it semi-annually, that would be twice a year. So those are some common values of N that you will see in various different compound interest problems. This is a very popular formula and is used very frequently in a variety of settings. In example 4, we are going to use the compound interest formula to look at Mrs. Solisman's situation here. We're looking at a situation using financial literacy. Mrs. Solisman invested $2,000 into an educational account for her daughter when she was an infant. The account has a 5% interest rate. If Mrs. Solisman does not make any other deposits or withdrawals, so she's not putting any more money in beyond the $2,000, nor is she withdrawing or taking money out of the account, she just allows the $2,000 to sit in this account for 18 years. If her interest is compounded quarterly, what will her balance be at the end of those 18 years, when the 18 years is up? So if we look back at the formula that we had A equals P times 1 plus r divided by n times, or actually raised to the n times t. We need to decide where to plug in all the numbers that they have given us. Well, we decided P for principal was the initial amount put into an account. In this case, the original amount of money put in the account is $2,000. So we're going to say A equals 2,000 times 1 plus, our rate is 5%. Our interest rate, R, is 5%. However, we are not going to plug in 5 for R. 5% as a decimal is 0.05. So we're going to take 0.05, her interest rate, and then we're going to divide that by n compoundings, which is how often the bank or business is paying her interest on this money that she's put into this account. Well, it states that her interest is compounded quarterly, so we're going to divide that 5% by 4. And then for our exponent, we're going to say 4 times 18. So I'm just going to put a little 18 right here. Now, the reason why I put 18 there is because she's leaving the money in the account for 18 years. Time is 18 years. So here's the deal. She's getting paid interest 4 times for 18 years. So the total number of interest payments is 4 times 18. Now, what we want to find is the value of A, the amount in the account after said 18 years. So what we're going to do is we're first going to calculate what the inside of our parentheses is equal to, because we follow order of operations and we always simplify within parentheses first. So if I take 1 plus 0.05 divided by 4, I divide the 0.05 by 4 first, then add 1 to it, and I get 2,000 times 1.0125. And 18 times 4, my exponent is 72. Therefore, she's paid interest 72 times over the course of the 18 years. And what I'm going to do is I'm going to take the 1.0125, raise it to the 72nd power, and multiply by 2,000. If I follow the correct order of operations there, raising 1.0125 to the 72nd power and then multiplying by 2,000, we get an amount of $4,891.84. This is the amount that Mrs. Solisman will have in her account after 18 years, given that she started with $2,000 in the account. In example 4, part B, we are going to look at what happens if Mrs. Solisman invests the same amount of money, $2,000, into the account for her daughter. She's still going to keep the money in the account for 18 years and have a 5% interest rate. However, this time the interest is going to be compounded monthly. We want to find out how that affects the outcome, how much money will be in the account after 18 years if the interest is calculated monthly. So here we go. We have 2,000 times 1 plus. Remember, 5% has to be converted to a decimal, which is 0.05. And this time, n is 12, since there's 12 compoundings in a year, or 12 months in a year. And we're going to then take 12 times 18, which is the number of interest payments that will occur over those 18 years. So if we simplify here inside of our parentheses, we're going to have 2,000 times 0.05 divided by 12 is 0.004 approximately, and if I add 1 to that, I get 1.004166667, and 18 times 12, my exponent, is going to be 216. In the last example, there were only, I think, 72 interest payments because she was only paid interest 4 times a year or quarterly. Since she's been paid interest in this example 12 times per year over the course of 18 years, that is 216 interest payments. So let's go ahead and see how that affects the outcome or total balance of the account after 18 years. So what I'm going to do is I'm going to take 2,000 times 1.004166667 and raise that to the 216th power, and we get $4,910 we'll say 02 or 2 cents if we round to the nearest cent. Now, you'll notice that our amount in the account after 18 years, when our interest is compounded monthly, is not that much greater than if our interest is paid out quarterly. I think if I take the difference between the two numbers, it's about $18.18 if I subtract the answers from Part A and Part B. So by having a bank that pays me interest monthly rather than quarterly, we're actually making an extra $18.18, which over the course of 18 years is really roughly approximately $1 per year extra that we're making from this investment rather than the investment we made in Part A. In example 4, Part C, Mrs. Solisman is making the same $2,000 investment into the educational account for her daughter at the same rate of 5% for the same amount of time for 18 years. But this time she wants to know what will happen if she compounds her interest daily. Now, we did not talk about what this represents, daily compounding. Since T is in years and our interest rate is being compounded daily, there are 365 days in a year. So therefore, our end value here is 365. She's going to be paid interest on that $2,000 every single day for 18 years. Let's go ahead and see how this affects the outcome or the end result, the amount in her account after those 18 years. So using the compound interest formula, we still have the same principal or initial amount invested, $2,000. And then I have 1 plus my interest rate this time, that 5% is being divided by 365. And we'll raise that to this 365 times 18. Since she's being paid interest daily for 18 years, that gives me 6,570 interest payments over the course of the investment, which, if I simplify that, and I take 0.05 divided by 365, and add that to 1, I get 1.000136986, and like I said previously, multiplying 365 times 18 gave me 6,570 interest payments over the course of the investment. Now, what I'm going to do is raise the 1.00136,986 to the 6,570th power, and I get 2.4594515. So I'm going to have 2,000 times 2.459451511. I'm using all these decimal places to get the most accurate answer I possibly can. And I get an amount of $4,918.90 after 18 years. Now, comparing this to our last example where we had our interest compounded monthly, the difference between the compounding monthly and compounded daily only amounted to a roughly $8.88 over the course of 18 years, which really is not that much. You're going to want to gain as much money as possible, but I really don't think that $8.88, depending on the person, is not that big of a deal. You're not really gaining that much from having the interest compounded daily versus monthly. In example 4 guided practice, we are still dealing with the issue of financial literacy. This time, Mr. Bourne is investing $5,000 into a savings account at his local bank. The account has a 3% interest rate. If Mr. Bourne does not make any other deposits or withdrawals, what will the account balance be after 11 years if the interest is compounded monthly? What I would like you to do is go ahead and work out this problem and select your answer A, B, C, or D, and then press submit for your answer.